Good morning, everyone. Yeah, our class has passed the half time. Yeah, time is so flying. Yeah, we have already learned the simple harmonics and traveling waves and wave optics and ring optics. Yeah, like step by step. Yeah, like the following chapter is based on the last chapter. Yeah, if you like observe very carefully. And today, yeah, we will start to learn something about electric fields and forces. Okay, let me share my screen and let's start this class. Okay, let's start this class. Yeah, today we will talk about, oh, sorry. We will talk about electric fields and forces. And this is today this chapter's goal, to develop a basic understanding of electric phenomena in terms of uh, charges, forces, and fields. Yeah, those two terms, we will learn what is charges, what is forces, and what is fields, and how to use those three things to understand the phenomenon in the real world. Yeah, actually, you can see here, there is an image put it here. Some at the beginning, at the first set, you will be very confused why there is a being, there is a flower. It is related to electric fields and forces. It's like difficult to imagine, am I right? Actually, yeah, you can see when the beings usually, if they search the best flower, they will send some information to the outside, and then form a field, and then they can choose choose the best flower to fade. Yeah, I will talk about this later in this class. Okay, yeah, so just remember, this chapter's goal is just develop a basic understanding of electric phenomena in terms of charges, forces, and fields. Okay, let's talk about what are these exactly. Okay, this is today's goal. Firstly, let's try to understand charges and forces. And then let's explore charges, atoms, and molecules. And finally, we will learn the Coulomb's law. Yeah, this is a very important law, Coulomb's law. Yeah, and okay, let's start today's class. And before we start today's class, let's try to looking ahead to preview the chapter 20. Firstly, the charges and the Coulomb's law. Let's talk about what is it. You can see here there is a very interesting a situation. A cone, yeah, there is a cone rubbed through your hair attracts a thin stream of water. Like the charge model of electricity explains this force. Yeah, usually if you especially in the winter, if you rubs your hair very hardly, and then you will see your hair will uh, flying. Yeah, this is a similar thing. You can explain this using charge model. Yeah, we will explain it later. And also you will learn to use Coulomb's law to calculate the force between two charged particles. Yeah, this law, using this law, we can calculate the force between two charged particles. Okay, and then we will learn something about the electric field. Like charges create an electric field around them. In thunderclouds, the field can be strong enough to ionizing air, causing lightning. Yeah, you can see those lightning. Actually, the reason for this lightning is just like the field. The electric field is very strong and causing lightning. And you will learn how to calculate the electrical field for several important arrangement of charges, yeah, in this class. Okay. Uh, yeah, we will also learn like the forces in electric fields, like charge the DNA fragments in this electrophoresis gel. As you can see, here are some gels here. Yeah, and are separated for analysis as they migrate at different rates in an applied electric field. Yeah, this is some applications. Yeah, because of the electrical fields exist, and there are some like forces in electrical fields, and then those gels can be separated for analysis. Yeah, you will learn how electric fields act exert uh, forces and torques on charged particles. Yeah, you will learn those things. Yeah, also in chapter 20. And before we talk about chapter 20, I want to you guys like look back something like vectors and components. Yeah, actually vectors and components are very important, like basic uh, things in for learning physics. I think also for learning many things like mathematics, maybe yeah. And in sections 3.2, you studied how a vector could be resolved into its component vectors. Yeah, you can see these vectors, yeah, can be can be divided to different vector like ax and ay. Ax along the x-axis and ay along the y-axis. Yeah, and yeah, like electric forces and electrical fields are vectors, so you will need to use vector components to solve electric forces and field problems. Yeah, this is you will use these ideas to resolve some problems. You learned that a vector A can be represented as a sum of its component vectors ax and ay. Yeah, you you should have already learned these things. If you forgot or if you like think you don't learn it before, so you need to search and uh, or look back the section 3.2 to check if to learn what is this. Yeah. Okay. Let's stop to think this question. The tension in the rope is 100 Newton. Given that sin 30 degrees is 0.5 and cosine 30 degree is 0.87, and like the x and y components of the tension are what? You can see this is this is 100, and it will have two components. One is y and the other is x. And for the y, it is positive, am I right? But for the x, it is negative. So what you just need to find out which one is negative. Yeah, this one is, and this one is negative for the x, am I right? And here for the x, it is equal cosine 30 degree multiple 100. So it should for the x it should negative 87, and for the y it should be positive like multiple 100 like 50. So the answer should be A. Does it make sense to you? Yeah, this question just let us to review the vector and the components of the vector. Yeah, yeah, we will use this in today's class. And okay, let's start today's class, and let's talk about the section 20.1, like charges and forces. And yeah, since from chapter 20, I will put some videos here, and you can review that. And some videos I have already give you in the reading quizzes, and some I didn't, and you can check these videos by yourself. I will not play these videos in the class to save time. Okay, let's continue. Like two objects rubbed together can cause a force or a spark. You can see if in the ancient time, like people use like the stick and two stick to gather fire. Yeah, because if you rub two stick and it can cause a spark. And scarfing your feet on a carpet can produce a little spark if you touch a doorknob. Yeah, like you can try that, especially in winter because it is very dry. If you touch a door knob and scarfing your feet on carpet can produce a little spark. And running a plastic car through your hair can result in a force that can pick up little pieces of paper. Yeah, you also can try that. This is some interesting science phenomenon. Yeah, because like you can see, rub this. You rub your feet with on a carpet, and here you like rub the curve like with your hair, like it will produce a force or a spark. Yeah, our first goal is to develop a model of electric phenomena in terms of charges and forces. Okay, let's quick review some experimenting with charges. Like the major tools in a modern style laboratory for studying electricity include a number of plastic. Yeah, I think these things you must have learned in the high school and also like in the college. Yeah, co college physics one. I'm not sure, but this one, this experiments is very fundamental experiments. Yeah, like there are some major tools you can use it to study electricity. Yeah, it includes like a number of plastic and a glass rods, each several inches long. This can be held in your hand or suspended by threads from a support. Yeah, for example, here there is a thread, and here there is a rod. Yeah, like that. And this is the first thing. And the second thing is a piece of wool and silk. Yeah, some pieces of wool and silk. And the next thing is small metal spheres, an inch or two in diameter, on wood stand. Yeah, those three things like are used for studying electricity in modest laboratory. And let's check the experiment one. Yeah, take a plastic rod. Yes, here is a plastic rod, and that has been undistributed for a long period of time and hang it by a string. Pick up another undistributed plastic rod and bring it close to the hanging rod. Nothing happens to either rod. Yeah, you can see if you put like a hang a rod by a thread and let this rod still here, and then you hold the other one, and you bring those two close to each other. Nothing will happen to either rod. Yeah, and why? There are no special electrical properties to these undisturbed rods. We see that they are neutral. Yeah, you can see there are no special electrical properties here. Yeah, so we see in this situation like those those rods are neutral. And let's check see the other one. Vigorously rub both the hanging plastic rod and the handheld plastic rod with wool. Now the hanging rod moves away from the a handheld rod. When you bring the two close together, rubbing two glass rods with silk produces the same result. The two rods repel each other. Yeah, you can see if you like a rub like those one and those one with wound or with with wound, and you can see they will move away. Yeah, because they have the. I will explain that later. And if you rub two glass rods with silk, it will have the same result. Yeah, the two rods repel each other. Let's see why. Rubbing a rod somehow changes its properties so that forces now act between two such rods. We call this process the rubbing charging. We call this process the rubbing. We call it charging. And see that the rubbed rod is charged. Yeah, this produce we call the rub. The rubbed rod is charged. Or that it has acquired a charge. Yeah, that we call this process the rubbing charging. Yeah, and we and see that the rubbed rod is charged, or it has acquired a charge. Yeah, this is a definition for the charging and being charged or acquired a charge. Yeah. Okay. This experiment shows that there is a long range repulsive force between two identical objects charged the same way. Yeah. There is a sorry. Yeah. There is a long-range repulsive force between two identical objects charged the same way. Yeah, that makes sense to you. Yeah, because actually, after you rub this rod and this rod with like a wound, and it has the same charge, you charge those two the same way, and there will be a long-range repulsive force and make them get away with each other. Does that make sense to you? Okay. Okay, let's see some those experiments with chargers. The electric force is a force between. Yeah, what is electric force? The electric force is a force between charged objects. The gravity is also a long-range force, but it is always attractive. Yeah, you can see two things they always be attracted with each other. Yeah, it also long-range force. The electric force can be repulsive and attractive. Yeah, if it is if the electric force sometimes it will be repulsive and sometimes it will be attractive, and we will talk about it later. When it will be repulsive and when it will be attractive. Okay, let's continue. Let's see the other experiment. Yeah, bring a glass rod that has been rubbed with silk close to a hanging plastic rod that has been rubbed with wool. Those two rods attract each other. Yeah, you will see, like if you do this experiment, you will see this situation. Like if you rubbed a glass rod with silk and rub a plastic rod with wool, and these two rods attract with each other. Let's see why. We can explain this experiment as well as experiment 2 by assuming that there are two different kinds of charge that a material can acquire. Yeah, we define the kind of charge acquired by a glass rod as positive charge. Yeah, actually charge has different situation when one is positive charge and that acquired by a plastic rod as negative charge. Then these two experiments can be summarized as like charges Yeah, positive, positive, yeah, positive, positive, or negative, negative, which means they have the same properties and they will be repelled with each other. They will get away with each other. Exert repulsive forces on each other. Yeah, well, opposite charges. Yeah, like a positive, negative. One is positive, the other is negative. Exert attractive forces on each other. Yeah. Yeah. So like there will be two different kinds of charge. The atom material can acquire. One is a positive charge, the other is like um, a negative charge. And yeah. And for the so for summarize, like it's there are two different charges. Yeah, one is like charges, which means like two things they have positive positive or negative negative. Or there is a opposite charge, like one is positive, the other is negative. Yeah. Okay, let's continue. Let's check the other experiment. Yeah, if two rods are held farther from each other, the force between them decreases. I think this is easy to understand. If two rods are held farther from each other, which means the force, the electric force will decrease. Yeah, and the force between them decrease because they are far, so it's obvious. Yeah, the strength of the force is greater for rods that have been rubbed more vigorously. Yeah, I think this one is also easy to understand. Like if the stress of the force is greater, if you rub these rods very vigorously, which means you there are more charges generate. That make it there will be more charges. Does that make sense to you? Okay. Like yeah, there are some like explanation, like interpretation, like the gravitational force, the electric force decreases with the distance between the charged objects, and the greater the charge on the two objects, the greater the force between them. I think this one, yeah, it's easy to understand. Okay, let's see the other thing. We call it visualizing charge. Yeah, you can see here. A chart diagram gives a schematic picture of the distribution of charge on an object. You can see here. This is a charge. This is a charge diagram. Like a negative charge is represented by minus signs. You can see here. There are some minus signs, and usually the negative charge is represented by minus signs, and the positive charge is presented by plus signs. Yeah, here. One is minus signs. The other is we represent equal amounts of positive and negative charge by drawing the same number of plus and minus signs. More charge is represented by more like a more plus or minus signs. Yeah, this is just a chart diagram. Yeah, like for to sometimes for like representing the theory very clearly, we need to draw the charge diagram to explain those things. Okay, and let's see the other experiment. And start with a neutral uncharged high-in plastic rod and a piece of wood. Rub the plastic wood with the wound. Then hold the wound close to the rod. The rod is extracted to the wound. Yeah, let's explain this. Like for experiment 3, we know that the plastic rod has a negative charge because the wound attracts the rod, and the wound must have a positive charge. We know that, yeah. Like one have the negative charge, the other will have the positive charge. If in this situation, like those two will be attracted to each other. Yeah, with here are some class video. You can check this like after this video. Yeah. Like which means if this this experiment mainly tells us if two atoms are attracted with each other, there must be like one has a negative charge, the other has a positive charge. Yeah. Okay. Like when a rod is rubbed by wind, not only does the plastic rod acquire the negative charge, but the wind acquires a positive charge. Yeah, you can see if you actually like a neutral object is not something with no charge. Yeah, just pay attention. A neutral object is not something with no charge. Yeah, sometimes like some students may think as a neutral object maybe it's no charge, but it's not. Yeah, a neutral object contains equal amounts of positive and negative charge, which means you can see this at the beginning in the initial situation for the wound and for the plastic, and those two are like a neutral objects. Yeah, that doesn't mean there is no charge. Actually, yeah, for this wound and for this rod, like the amounts of the positive and negative charge is equal. Yeah, they equal with each, they equal like understand? Yeah, yeah. Did I tell it clearly? Yeah, so neutral actually means that they each have equal amounts of positive and negative charge. Yeah. Okay. An object becomes positively charged if the amount of positive charge on it extends the amount of negative charge. Yeah, which means if an object becomes positively charged, which means like the amount of positive charge on these things extends exceeds the amount of negative charge. Yeah, yeah. Like similarly, an object is negatively charged when it has more negative charge on it than positive charge. Yeah, similar thing. Yeah, that makes sense to you. Okay. Yeah, this is an experiment like a if we rub the plastic and the wound together. As we do so, negative charge moves from the wound to the rod, like which means the most like a negative charge to the rod and most positive charge to the wound. Yeah, like this leaves the rod with actual negative charge. The wound is left with more positive charge than negative. Yeah, in a charge diagram, we draw only the excess charge. This shows how the rod and wound acquire their charge. Yeah, because this is a positive, so we just draw the positive. This one is a negative, like the negative is like axis. Yeah, more than like the positive, so we draw the negative. Okay. The law of conservation of charge states that charge is neither created nor destroyed, only transferred from one place to another. Yeah, just pay attention. The charge is neither created nor destroyed, only transferred from one place to another. Like the one very simple example, like when you charge your phone, it's not like something like a the electric is not created. It's just like the electric is just from the electric power station from your house or from your apartment. Yeah, from yeah. It's not like the charge is not created or destroyed. It's just like a transfer from one place to another. If a certain amount of positive charge is staying somewhere, an equal amount of negative charge must appear elsewhere so that the net charge does not change. Yeah, so the net charge will forever keep the same. Yeah, like that makes sense to you? Yeah, the results of our experiments and our interpretation of them in terms of positive and negative charge can be summarized in the following charge model. Yeah, let's talk about the charge model here. Yeah, like the charge model, like the basic postulations of our model are like a frictional force, such as firstly, let's talk about one term like frictional forces, such as rubbing and add something called a charge to an object or remove it from the object. Yeah, like we call this frictional rubs and frictional forces. And the process itself is called charging. More vigorous rubbing produces a larger quantity of charge. There are two kinds of charge, positive and negative. Two objects with like charge, positive, or negative, exert repulsive forces on each other. Two objects with positive charge, yeah, one is positive, the other is negative, exert attractive forces on each other. We call these electric forces. Yeah, does it make sense to you? Yeah, which means there are like the process like to using friction force to charge one atom. We call it charging. Like a more vigorous rubbing produces a large quantity of charge. And for the charge, there are two kinds of charge, positive and negative. And two objects with like charge, yeah, like charge means one is positive, the other is also positive, or one is negative, the other is also negative, exert repulsive forces on each other, which means they will like get away with each other. And two objects with opposite charge, like one is positive, the other is negative, exert like attractive forces on each other. We call this, yeah, we call those like charge and opposite the charge, or like these we call these electric forces. Yeah, that makes sense to you. Okay, the force between two charged objects is a long range force. The magnitude of the force increases as the quantity of charge increases and decreases as the distance between the charges increases. Yeah, this is the features for a long range force. Yeah, gravity, we talk about gravity is also a long range force. Okay, the neutral objects have an equal mixture of positive and negative charge. Like we talk about a neutral object is no like objects, they have the charge, but they have an equal mixture of positive and negative charge. Yeah, the rubbing process charges objects by transferring charge from one to the other. Like the objects acquire equal but opposite charges. Yeah, like the rubbing, this action, like a process, charges the objects by transfer charge from one to the other. Yeah, and the objects acquire equal but opposite charge. Yeah, charge is conserved. It can be created. It cannot be created or destroyed. Like it is conserved. It is just can be transferred but not be created or destroyed. Okay. Okay, let's continue. Let's try to know what is insulators and conductors, like by this experiment 6. You can see charge a plastic rod by rubbing it with warm. Touch a neutral metal sphere with the rubbed area of the rod. The metal sphere then repels a charged hanging plastic rod. The metal sphere appears to have acquired a charge of the same sign as the plastic rod. Yeah, this is the experiment we do. There is a metal sphere acquires charge. Yeah, and place two metal spheres close together with a plastic rod, connecting them. Charge a second plastic rod by rubbing, and touch it to one of the metal spheres. Afterward, the metal sphere that was touched repels a charged hanging plastic rod. The other metal sphere does not. Yeah, which means like when you do these things, when you do this lab, please to firstly place two metal spheres and connect with a plastic rod, and then you charge this plastic rod by rubbing and touch it to these metal spheres. Yeah, afterwards, these metal spheres that was touch repels a charged hanging plastic rod. Yeah, it will repel this one, but this one they will not. This metal sphere does not like repel a charged hanging plastic rod. Let's explain why. Yeah, repeat. Let's finish this experiment and tell us why and talk about why. Repeat experiment 7, like with a metal rod connecting the two metal spheres. Touch one metal sphere with a charged plastic rod. Afterward, yeah, you can see. Repeat this experiment, but the difference is you replace the this one with a metal rod, and then like touch one metal sphere with a charged plastic rod. Afterward, both metal sphere repel a charged hanging plastic rod. Yeah, like you can see charge can be transferred from one object to another only when the objects touch. Yeah, when two objects touched, and then charge can be transferred from one object to the other. Discharging is removing a charge from an object, which you can do by touching it. Yeah, there is another item, discharging, which means removing a charge from an object. You can do it also. Also, you can do it by touching it. Conductors are those materials through or along which charge easily moves, like this metal rod. And insulators are materials in which charge is immobile. Yeah, like those plastic rod. Yeah, and glass and plastics are insulators, but metal is conductors. Yeah, you can see since if you connect those two like metal sphere with metal rod, when you charge this metal sphere, and this metal rod will also be charged, and then those metal sphere also will be charged because the metal rod it is a conductor, but the plastic rod it is insulators. Yeah, when you charge this metal sphere, this plastic rod will not be charged. Yeah, by just only touching. Yeah, if you want to charge this plastic rod, you need to rubbing it. Yeah, and if this one will not be charged, and this one obviously will not be charged. Yeah, this plastic rod is insulators. Yeah, that makes sense to you. Okay, this is the insulators. What is an insulator? And what is a conductor? The conductors are like those materials through or along which charge easily moves. The insulators are materials in which charge is immobile. Yeah. So glass and plastics are insulators, but metal is a conductors. Yeah, that's the reason why the experiment 7 and experiment 8 happens. Yeah. Okay, let's continue to talk about the charge model. This new information allows us to add more postulates to our charge model. Like there are two types of materials. Conductors are materials through or along which charges easily moves. Insulators are materials on or in which charges remain fixed in place. Charge can be transferred from one object to another by contact. Yeah. We talk about that. Okay, let's talk about one example, like transferring charge. In experiment 8, like touching a metal sphere with a charged plastic rod caused a second metal sphere connected by a metal rod to the first to become charged with the same type of charge as the rod. Use the postulates of the charge model to construct a chart diagram for the process. Yeah, reason we need we need the following ideas from the charge model. Yeah, the first one is the charge is transferred upon contact. The plastic rod was charged by rubbing with wound, giving it a negative charge. The charge doesn't move around on the rod like isolator, but some of the charge is transferred to the metal upon contact. Yeah, metal is a conductor. Yeah, once in the metal, which is a conductor, the charges are free to move around. Yeah, conductor, the charge are free to move around. And for the like a plastic rod, and yeah, you cannot just by touching to charge this plastic rod. But you can rubbing the plastic rod, which can transfer the like friction like force to electric force. Yeah, then to charge the plastic rod, and yeah. It will give it a negative charge. Yeah, the charge does not move around the rod. Yeah, it only like this rod touch the metal sphere and then transfer the charge to the metal sphere. Yeah, and like charges rebel, because like yeah, let's talk about like charge rebel. Yeah, because the like charge rebels, these negative charges quickly move as far apart as they possible can. Some move through the connecting metal rod to the second sphere. Consequently, the second sphere acquires a light negative charge. The repulsive forces drive the negative charges as far apart as they can possibly get, causing them to end up on the surfaces of the conductors. Yeah, that makes sense to you. Yeah, you can see this charged insulating rod. This is a metal ball. Like the charge is transferred to the metal sphere upon contact. The charge on the rod away from the contact point stays fixed. This charge repel. These charges repel each other, and the repulsive forces cause the charge to spill out over the surface of the conductor. Yeah, this charge is very extremely fast. Yeah, and once the charge is placed on the conductor, it rapidly distributes itself over the conductor's surface. Yeah, like let's talk about one atom, like electrostatic equilibrium is a condition in which the charges on an isolated conductor are in static equilibrium with charges at rest. Yeah, this is like a static equilibrium. This is a condition. Like in this condition, the charges on an isolated conductor are in static equilibrium with the charges at rest. A conductor is in electrostatic equilibrium with the expectation of the brief interval during which charges are adjusting. The moment of charge is extremely fast, so the interval is very brief. You can just see. So, so which means why like the electrics is very dangerous. Sometimes if you just touch like sometimes by accident touch the wires and some dangerous thing and it you will like it will cause you to die in a very immediately time. So just be careful when you like do some like electrical thing. Yeah. Okay, let's view some quick check questions. Consider two objects A and B. Object A has a net charge while B is uncharged. Based on this information, it must be true. Like A is a conductor and B is an insulator, and A is an insulator, B is a conductor. A and B are both in insulator, B blah blah blah. So I think this one, guess which one is the right thing. Yeah, actually for this question, like the answer should be E. There is not enough information to tell. Actually, yeah, you cannot tell like this object is conductor or insulator like by if it has a net charge uh, only like if it has a net charge or it is uncharged or charged. You cannot like tell if it is a conductor or insulator like by these features. Yeah, sometimes something is uncharged. That doesn't mean like it cannot be charged. Doesn't make sense to you. Yeah, sometimes it has a net charge. It doesn't mean like it can be it is a conductor such as a plastic rod. Yeah, it has a net charge sometimes. Yeah. Okay. Let's talk about polarization. Polarization. Like the charge polarization is the slight separation of the positive and negative charges in a neutral object when a charged object is brought near. You can see like the neural sphere contains equal like amounts of positive and negative charge. Actually, yeah, a neural sphere like contains yeah such like this. Yeah, the negative charge is attracted to the positive rod. Yeah, this leaves behind the positive charge on the other side and the negative charge in this side. This situation we call it charge polarization. Yeah, does it make sense to you? Like which means all the negative charge goes this way and all the positive charge goes this way. Yeah, like this situation called charge polarization. And here are some like videos you can check. Yeah, you can check those videos after this class. Okay, let's continue to talk about polarization. Yeah, the negative charges at the top of the sphere are more strongly attracted to the rod than the distant positive charges are repelled. So there is a net attractive force. Yeah, because you can see, this rod is a positive, and then like this sphere has the charge polarization situation. Like all the negative is here and all the positive here, and because the distance, yeah, the net force should be like a negative. Yeah, so there is a net attractive force. Yeah, that makes sense to you. Yeah, the positive charge on the sphere is far from the rod, so it is weakly repelled by the rod. So the net force is toward to the rod. Yeah, the polarization force arises because the charges in a neural object are slightly separated, not because not because the objects are oppositely charged. Yeah, that makes sense to you. Yeah, the polarization force arises because the charge in a neural object are slightly separated, not because objects are positively charged. Yeah, like not because like the like they have the more like a negative charge or more positive charge. It's just like the positive charge far from like this side. That makes sense to you. Like the polarization force between a charged object and a neural one is always attractive. Yeah, a charged and a neural one is always attractive. Does it make sense to you? Yeah, because the polar force between a charged object, yeah, this is a charged object, and a neural one is always attractive. Yeah, um, because like if this charged one is a positive like charge, it has a positive charge, which means this negative charge on this sphere is close to a rod, and it will always have the always like attractive, doesn't make attracted with each other. Doesn't make sense to you? Okay. Let's continue to talk about some like quick check questions. Charged glass and plastic rods hung by threads. An object attracts the glass rod. If this object is then held near the plastic rod, it will, yeah, which one? Attractive the plastic rod or repel the plastic or not affect the plastic rod or either A or B. That's not enough information to tell. Let's talk about charged glass and a plastic rod hang by object attracts the glass rod if this object is then held near the plastic rod, it will. One is glass rod, the other, which means this object attracts the glass rod, which means it has the a positive charge. So, even this, we cannot, the answer is either A or B. There is not enough information to tell. The object could have plastic charge, which would repel the plastic rod, or it could be neutral and attract both charge rods. Does it make sense to you? If this objects has it is a neutral objects, it can attract the glass or attract the plastic. But if it is sometimes it will have the similar charges with opposite charge with plastic glass rod, but we don't know if the glass and the plastic rods have the same charged situation. Does it make sense to you? So there is not enough information to tell. Okay, let's talk about this one. A rod attracts a positively charged hanging ball. The rod is what? And you can see here, the ball is positive, and this rod is attracted with. So, which one is it? So, which means it can be negative. If it is negative, this rod is negative, it will be attractive. Am I right? But sometimes it can be, if it is neutral, it also can be attracted, because if it is neutral and it can have the polarization phenomenon, and the negative will be here. The negative charges will be here. The positive charge will be here, and then it will. So the answer should be either B or C. Does it make sense to you? Let's talk about the other one. The metal spheres 1 and 2 are touching. Both are initially neutral. There are some. If the charged rod is brought near, which means the sphere 1 will have the polarization situation. So the negative charge will be here, and the positive charge will be here. Am I right? So the similar thing, the negative charge will be here, the positive charge will be here. And because the metal sphere is a conductor, so as the time passing, all the negative charge will be here, and the positive charge will be here. Does it make sense to you? At the time. And for now, and after the charge rod is then removed, which means the polarization phenomenon will disappear, and so the positive and the positive charges, the negative charge and the positive charge, they will rearrange because those two are attracted with each other, so they will, the negative will go here, the positive will go here, and then those two will be reach to a equilibrium situation, back to the original one. So which means this one will become neutral, and this one will become neutral. To reach equilibrium stations. Status. So the answer should be E. That makes sense to you? Because let me explain one more time, to make it clear. Yeah, when the rod is brought near, which means those two metals will have the polarization situation. All the like negative will be charges will be here, positive will be here, and then but after you remove this charge rod, and then this polarization situation will disappear, and those two like different charge will mix with each other, and then those two like those two metal sphere will reach to a equilibrium, and after they separate quickly, yeah, you can see those like processes are very quickly to reach a equilibrium and then be separated. So which means this will be zero, this will be zero. That makes sense to you? Okay, let's talk about the other one. Yeah, this is an interesting one. Like, yeah, you can see metal sphere 1 and 2 are touching. Both are initially neutral. Then there are 3 steps. The charge rod is brought near. The spheres are separated. The charge rod is then removed. Yeah, you can see those one and those one are different. Yeah, this one, the first one is the rod is after like the charge rod is brought near, and then the rod is removed, and then the sphere are separated. But here, like the charge rod is brought near, and the sphere are separate, and then the charge rod is be removed. So which means after the charge rod is brought near, and here will be negative, here is positive, and then separate those two, which means those will be will be will have much more negative charges. Those will this will have much more like positive charges. Yeah, it will be go to negative, will be go to positive. Does it make sense to you? So, which means the Q1 is negative, Q2 is positive, and then you remove you remove this one. Yeah, it doesn't matter. Yeah, that makes sense. It will keep this situation. Okay, so yeah, the answer is C. Yeah, you can see the net charges is obtained if contact is broken while the sphere are polarized. This is charging by induction. Yeah, does it make sense to you? Okay, let's check this question. Identical metal spheres are initially charged as shown. Spheres P and Q are touched together and then separated. Then spheres Q and R are touched together and then separated. Afterward, the charge on sphere R is what? So let's initially P is 4 NC and Q is negative 2 NC, and which means after those two touched, and the total will be 2 NC, and two spheres share 2 NC, so one will be 1 NC, 1 NC, and then after that Q and R touched, and 1 NC and negative 1 NC, which means it will be neutralized, and then the Q will be 0 NC, R also it will be 0 NC, so the answer should be C. Does it make sense to you? Okay, yeah, yeah. What do you need? Just like firstly let P and Q plus together divide 2, which means like one have which charge, and then after that Q and R plus and divide 2, yeah, which is 0. Okay, let's continue. And okay, let's talk about charges, atoms, and molecules. Okay, and an atom has a dense, positively charged nucleus. Yeah, actually, for this section, yeah, there are so many like definitions, so many like yeah, definitions and theory things, and hope you will not be confused. If you have any question, just let me know. Yeah, okay. An atom has a dense, positively charged nucleus. Yeah, you can see here. This is this. Oh, sorry. Yeah, this whole thing is a atom, and this atom has like a dense positively charged nucleus. This is a nucleus. And these nucleons containing positively charged protons. You can see positively charged protons and neutral neutrons and some neutral neutrons. And this nucleus is surrounded by the much less massive orbiting negatively charged electrons. Yeah, this is electrons. That from an electron cloud. Yeah, this is an atom. Charge like mass is an inherent property of electrons and protons. Yeah, like electrons and protons is has an inherent property. It is charge. Yeah, this is an atom. Let's continue to talk about an atomic view of charging. Yeah, electrons and protons are the basic charges in ordinary matter. There are no other sources of charge. An object is charged if it has an unequal number of protons and electrons. Yeah, which means if it is equal, like the protons and if protons and electrons has an equal number, and this means an object is neutral. Yeah, it is not charged. Yeah. And an object is charged if it has an unequal number of protons on electrons. Yeah, most microscopic objects has an equal number of protons and electrons. Such objects are electronically neutral. Yeah, we call it electronically neutral. Objects gain a positive charge not by gaining protons, but by losing electrons. Yeah, like objects gain a positive charge not by gaining protons, but by losing electrons, because it is losing electrons, which means the electrons less, and so it will have a positive charge. Yeah, protons are extremely tightly bound within the nucleus, but electrons are bound much more loosely. Yeah, which means like objects usually it's easy to lose electrons for an object. Yeah, because protons are extremely tightly bound with nucleons. Yeah, you can see here the protons are extremely tightly bound within the nucleus, but electrons, yeah, those electrons, they just walk around orbiting surrounded by these nucleons, and it is easy to electrons are bound much more loosely. Yeah, and longylation is the process of removing an electron from the electron cloud of an atom. Yeah, what is longylation? What is longylation? Longylation is the process of removing an electron from the electron cloud of an atom. An atom that is missing an electron is called a positive ion. Yeah, because the atom has lost one electron, giving it a net negative charge. If atoms that can accommodate an extra electron become negative ions, like the atom has gained one extra electron, giving it a negative charge. Yeah, that makes sense to you. Okay. Molecular ions can be created when one of the bonds in a large molecule is broken. Yeah, you can see if there is a electrically neutral molecule. Yeah, this is atoms, and those atoms are bound are bonded, and after give those atoms friction, and those bonded were broken by friction. So like this half of the molecule lost an electron as a bond broken. Yeah, it will become positive molecular I. And this half of the molecule gained an extra electron as the bond broken. So those things, those parts become negative molecular ion. Yeah. So but those two, if it connected with each other, connect together, it will be neutral. But because when it broke, this one lose electron. So this one become positive, this one become negative. That makes sense to you? Okay. Like rubbing and friction often cause molecular bonds at the surface to break. Charging occurs when negative ions transfer to one material, leaving positive ions on the other. Yeah, that's a reason. Do you know like why when after you rubbing the plastic rod, when you're rubbing the hair, when you're rubbing some like a silk and a wound, it will have the it will have the it is a charging process. That's here. That's a reason. Yeah, because the atoms in the plastic rod, in the wound, in your hair, yeah, it will break the bonds between the atoms will is broken by the friction, by rubbing, and then there will be positive molecular ion and negative molecular ion, and then it will the charging occurs when negative ion transfer to one material, leaving positive ions on the other. Yeah, the when you rubbing the plastic rod with silk, yeah, and the negative will transfer to wound, and the positive, yeah, will transfer to wound, and then the wound will have the trans yeah will have the positive thing, and the plastic rod will have the negative thing. Yeah, so sometimes it is opposite, but yeah, similar situation here. Yeah. Okay, a charge is represented by the symbol Q. Yeah, we just use Q to represent charge, and the SI unit, this is a international system unit, is Coulomb, Coulomb. Yeah, we short it as C. Yeah, the fundamental charge E is the magnitude of the charge of an electron or proton. Yeah, this is a constant value. Yeah, you can see this is the protons and electrons. Yeah, for the for one protons, and the mass for proton is this one, and the charge, yeah, for a proton the charge is E, and for the electron, yeah, the mass is this one, and the charge is the negative one. Yeah, for the electron, yeah, this one is a fixed constant value. Okay. Let's talk about the insulators and conductors to talk about why the insulators it, can transfer uh, charges, but a conductor why the conductor can transfer the charges, but insulator cannot. Yeah, you can see this is insulator insulator inside thing. Yeah, the electrons in an insulator are tightly bound to the positive nucleus and are not free to move around. You can see those things are valence electrons and tightly bound. Yeah, this is nucleons. I think there is a nucleus. Yeah, and this is core electrons, and this is valence electrons. Yeah, let me make it clear. Yeah, yeah, but the electrons in an insulate, yeah, in an insulator are tightly bound to the positive nucleon and are not free to move around. Charging an insulator may leave a pattern of molecular ions on the surface, but the patches are immobile. Are immobile. Yeah, you can see because the insulator, like the electrons are tightly bound to the positive nucleon. Yeah, so this nucleon, this electrons, yeah, no matter the Coulomb electrons or valence electrons, it is it are all tightly bound. It are not free to move around. So like charging an insulator may leave a pattern of molecular like ions on the surface, but the patches, yeah, those things are now immobile. Yeah, so which means it can be transfer charge. Yeah, okay. Like in metals, yeah, the outer electrons, you can see this is a positive ion cross. Yeah, you can see the valence electrons are free to move throughout the metal. Yeah, the outer electrons, valence electrons, are weakly bound to the nucleus. Yeah, I think it just a nucleus. It's just a typo. Sorry. And they are detached from their parent nucleon. And are free to wander through the entire solid, creating a scene of electrons, permitting an area of positively charged air cones. The electrons are highly mobile within the metal, but are still weakly bound to the air cones. Yeah, this is why the insulator is can be charged, cannot be charged, but the cannot transfer the charge, but the conductor can transfer the charge very easily. Yeah, and electric dipole. Let's talk about electric dipoles. Yeah, an electrical dipole is two equal but opposite charges with a separation between them. Yeah, you can see here. There is two equal but opposite charges with a separate between them. You can see the external positive charge attracts the atom's negatively charged electrons, pulling the electrons cloud slightly toward it. Yeah. Does it make sense to you? Yeah, you can see like yeah, because this external charge and like external positive charge, then the atom's negatively charged electrons like pulling the electron cloud slightly toward it. So all the negative will be here, and then the positive will be here. So those kind of atom will form an electric dipole, because you can see those are two equal but opposite charges with an separation between them. Yeah, there will be separation. Okay, yeah, you can see when the polarization is caused by an external charge, the atom has become an induced electric dipole. You can see the negative. Yeah, the negative will be here, the positive will be here, and it will become an induced electric dipole. Yeah, because the negative end of the dipole is slightly closer to the positive charge in this figure. The attractive force on the negative end extends the repulsive force on the positive end, because you can see this is the external charge, this is like positive charge. So this the external force on negative is bigger than the external on positive, because this one is a little further. So the net like the net force will toward the external charge. Does that make sense to you? Yeah. Okay. Yeah. Let's talk about the hydrogen bonding. Yeah, this is an application for, yeah, like some molecules have an asymmetry in their charge distribution that makes them permanent electric dipoles. Yeah, in a water molecule, bonding between the hydrogen and oxygen atoms results in an unequal sharing of charge that leaves the hydrogen atoms with a small positive charge. You can see with a positive charge. And the oxygen atom with a negative charge. Yeah, the electrons spend more time with oxygen than hydrogen. So the oxygen end is slightly negative and the hydrogen end is slightly positive. And a hydrogen bond is the weak bond. Yeah, between the hydrogen atom of one molecule of water and the negative oxygen atom in the second molecule. These weak bonds give water its stickiness responsible for properties such as expansion on freezing, the wide range of temperatures over which it is a liquid, and its high heat of vibrations. Yeah, this hydrogen bonding. Yeah, like yeah, the hydrogen is a weak bond between the hydrogen atom of one molecule of water and the negative oxygen atom in the second molecule. Yeah, these weak bonds give water its thickness. We know like the water is kind of liquid, and in high temperature it will vaporize it, and also like in unfrozen it also will expansion. So that's the reason why you can see the slightly negative oxygen is attractive to the slightly positive hydrogen of a neighbor. This water molecule forms hydrogen bonds with neighboring molecules. Actually, this bond is weak. Yeah, so which means the water can, yeah, can the shipment of water can be transferred. Yeah. Okay. Let's continue. Yeah, like hydrogen bonds are extremely important in biological system. The nucleotides, the four molecules, guanine, thymine, adenine, and chromatin on one strand of a DNA helix form hydrogen bonds with nucleotides on the opposite strand. The nucleotides bond only in certain pairs. This preferential bonding is due to hydrogen bonds. The positive hydrogen atoms on one nucleotide attract the negative oxygen or nitrogen atoms on another. Yeah, actually, the hydrogen bonding is very important in like a biological system. Yeah, because you can see here is some DNA like a double helix chain. Yeah, this hydrogen bonding can is a base pair of the two strands can join only in certain combinations, and yeah, those three in those guanine and crossing. Three hydrogen bonds join these bases, and two hydrogen bonds join the thymine and adenine like thing, and atoms compressing the bases. Yeah, which means that this hydrogen bonding like is the basic bonding, basic physical bonding for many like biological systems. Yeah. Okay. Okay, this is what we talk about like the atoms, like atoms charging and like let me see, atom charge and molecules, and atom charge and molecules, and some like features about why the insulators cannot transfer the charge, but the conductors can transfer the charge. Yeah, and what is electric depots, and what is hydrogen bondings, and how hydrogen bonding important in the biological systems. Yeah, this is what this section we talk about. And the next section we will talk about Colombian's law. Yeah, you can see a video about Colombian's law, and the Colombian's law. We have developed a model of charges and electric forces. Yeah, in section 1, yeah, 20.1. Yeah, in experiment 4, we found that the electric force increases for objects with more charge and decreases as objects are moved far further apart. Yeah, we have already talked about this in section 1. And the fourth law is Coulomb's law. We will use the magnitude of the charge, not the sign. Yeah, just the magnitude of the charge, Q, absolute Q. And yeah, magnitude, if two charged particles that have charges Q1 and Q2 are a distance r apart, the particles exert forces on each other of magnitude. Yeah, yeah, the like yeah, there are two charged particles Q1, QR, and the particles exert forces. Yeah, like on each other magnitude can be represented with these equations, where the charges are in columns. Yeah, C, and the key equal this one. It is a fixed. It is a constant. We call it electrostatic constant. These forces are an action and reaction pair, equal in magnitude and opposite in direction. Yeah. Okay, yeah, it is customary to round the key to this value. You can see here we the key is 8.99. We just round this value to 9. Yeah, and for all but extremely process calculations, and we will do so. Yeah, the forces are directed along the line joining the two particles. The forces are repulsive for two like charges. Yeah, if there are two like charges, means one is positive, the other is positive. Or one is negative, the other is positive, or negative. And this is two like charges, and the forces are repulsive. And if there are two opposite charges, like one is positive, the other is negative, and then the forces are attractive. Yeah, and you can see a video for this one. Okay, like Coulomb's law describes the force between two charged particles. Yeah, and this law applies only 2-point charges. Yeah, you can see from this equation there are only two charges. Okay, in the 2-point charges, objects can be considered point charges if they are much smaller than the distance between them. Yeah, if those two objects, yeah, are much smaller than the distance between those two, and we can consider this object as a point charge. Yeah. Okay. Yeah. Coulomb's law looks much like a Newton's gravity, except the charge Q can be positive or negative, so the force can be attractive or repulsive. Yeah, you can see here there are two negative charges, and the force will be repulsive. And there are there is two opposite charge. Like one is negative, the other is positive. It will be attractive. The direction of the force is determined by the second part of Coulomb's law. Yeah. Coulomb's law is a force law, and the forces are vectors. Yeah, electric forces, like other forces, can be superimposed. The net electric force on charge G due to all other charges is the sum of the individual's forces due to each charge. Yeah, you can see, like if there are multiple charges, and you can see the net will be the uh, all the electro forces plus together. Yeah, and each force is given by Coulomb's law. Yeah, you can see each one you can calculate by Coulomb's law. Okay. Okay, let's talk about one example. Yeah, like problem solving approach. Yeah, let's talk about first. Let's talk about one problem solving approach for like electric forces and Coulomb's law. Yeah, we can use Coulomb's law to find the electric force on a charged particle due to one or more other charged particles. Yeah, the strategy is identify point charges or objects that can be modeled as point charges. Think about the forces involved, their likely directions and magnitudes. Think about what you are trying to find and the likely details of the result. Yeah, then do a preparation. Create firstly like a identify point charges or objects, and then created a visual overview in which you establish a coordinate system, show the position of the charges, show the force vectors on the charges, and define distances and angles. Yeah, and then solve like using the Coulomb's law, like the magnitude of the force between point charges given by this equation. Yeah, use your visual overview as a guide to the use of this law. Show the direction of the forces, repulsive for like charges, attractive for opposite charge on the visual overview. And then draw the lenses of your force vectors according to Coulomb's law. A particle with a greater charge or one that is closer will lead to a longer force vector. I think this is obvious. If a particle with a greater charge or one that is closer, yeah, will lead to a longer force vector. Based on this equation. Yeah. Okay. Like when possible, do graphical vector addition on the visual overview, while not exact. It tells you the type of answer you should expect. Write each force vector in terms of its x and y components. Then add the components to find the net force. Use the visual overview to determine which components are positive and which are negative. Yeah, this is the process for resolving this kind of electrical forces and Coulomb's laws question. And check that finally check that your result has correct units, is reasonable, and answer the question. Yeah, this is a process for for solving those kind of questions. Okay. Okay, let's check this question. The charge of sphere 2 is twice that of sphere 1. Which vector below shows the force of 2 on 1? 2 on 1. This is 1 on 2. Yeah, actually, if we review these equations, you can see the force 1 on 2 equal the force 2 on 1, but just the different direction. So which one is the right answer? It should be. Yeah, the value should be the same, but just the different direction. Yeah, does it make sense to you? Okay, the answer should be. Yeah, you also can use Newton's third law to resolve this question. Okay, Let's check the other one. Let me check if okay. Yeah, the charge of sphere 2 is twice that of sphere 1. Which vector below shows the force of 1 on 2 if the distance between the sphere is reduced to r divided 2? Yeah, which means from this equation. Yeah, K equal what? Yeah, F equal K Q1 Q2 like R square. And yeah, you can see here the charge is the same, but the oh sorry, no, this one. Yeah, this one. Yeah. F equal K Q1 Q2 divide R square, and you can see the charge is the same thing, and only the distance reduced to r divided 2, which means here is yeah, and which means the force will become the four times compared with the original one, which means yeah, the C is the right answer. Doesn't make sense to you because the value will be four times. Oh, sorry. Yeah. The C is 2 times. Yes, C is 2 times. So you need to find the 4 times. So none of the above. Yeah, sorry about that. Yeah, none of the above. It's because you need to find the 4 times. There is no 4 times for that. Okay, let's check this one. Which of the 3 right hand charges experience the largest force? Yeah, you can see. Let's just write down the equation Q1, Q2, R like a square, and then you can see the first one like a QQ, which means K Q Q R. Yeah, with this one, this with 2 K Q Q. Yeah, because this is 2Q divide 4. Am I right? So and this one is 4KQQ divided 4, and yeah, and just remove this one. So this one and this one is equal. Am I right? And is the largest. Yeah, so Q and 4 and 4Q, yeah, are tied. Yeah, you should choose this one. Doesn't make sense to you. Okay, let's check the other one. Okay, let's check this question. In each of the following cases, an identical small positive charge is placed at the black dot. In which case is the force on the small charge the largest? Yeah, it asks you the largest one. So let's write the equation here. Which case the force on the small charge is K Q1 Q2 R square. So the first one is like KQ, like for example, this is X, and R, and this is K2QX. Yeah, because it is 2R. Yeah, this one is 2KQX. And this one is KQX. Yeah, which means this one is the biggest one, largest one. Does it make sense to you? Because yeah, this one is small compared with this one, and this one, this one is bigger than this one. So this one is the biggest one. Does it make sense to you? So yeah, the answer is C. Okay, let's check this one. And in which of the following cases an identical small positive charge is placed at the black dot? In which case is the force on the small charge the largest? All charges showing are of equal magnitude. Okay, yeah, you equal magnitude. Yeah, we can set it as QQ. Yeah, and then a small positive charge. This is X. Yeah, which means it will have the positive. It will yeah, this one will have this two together, and this one will have the like this one and this one. Yeah, and this one will have this one, and yeah, because it's positive, and this one will have like this one. So which means this one and this one is bigger than this one, because these two are like removed sub, like yeah, and this one is will plus together to yeah, but this one you can see, this one is close to this one is close to this, but this one is close to this, but further than this. That means this must greater than this one. Yeah, does it make sense to you? So the question is the answer will be A. Yeah, does it make sense to you? Okay. Let's continue to talk about this one. Yeah, the direction of the force on charge negative Q. Yeah, is which one? Yeah, which means this is negative, this will, and this is positive, and this one. But this one is further, so which means this one is much bigger. Yeah, bigger. So which means it will be right. Yeah. So the answer will be D. Does it make sense to you? Because Q, negative Q is slightly closer than positive Q. Yeah. Okay. Let's talk about this example. Yeah. Two positive 10 NC charged particles are uh, 2 centimeter apart on the x-axis. Yeah. Here there is one, and there is another one. It is 1, 2. Yeah, those two are 10 NC charged particles. Yeah, what is the net force on a 1 NC charged, positive NC charged midway between there is a 1. Yeah, what is the net force if charged particles on the right is replaced by a positive NC charge? If charge particle on the right, yeah. Like we will proceed using the steps of the problem solving approach 20.1. We will model the charged particles as point charges. Yeah. And the visual overview of the figure establishes a coordinate system and shows the force. Yeah, 1 on 3. Yeah, this is 3. Yeah, 1 on 3 and 2 on 3. Yeah. The top figure shows a positive 10 NC charge on the right. The bottom figure shows a negative, yeah, negative NC charge here. There is a positive, there is a negative. So I think the answer, the question is wrong. It is negative. Yeah, otherwise, yeah, the original is positive. It should be negative. Does that make sense to you? So the second one should be this one. Yeah. Okay. Let's try to solve this question. Electric forces are vectors, and the net force on Q3 is a vector sum, like F net equal F1 on 3 plus F2 on 3. Yeah. And the charges Q1, Q2 each exert a repulsive force on Q3, but these forces are equal in magnitude and the opposite in direction. Consequently, yes, F net equals 0, because yeah, this one is the same thing. Yeah, we know like F equal K Q1 and Q3 like R square. Actually, this is the same thing, and Q1 and Q2 is the same thing, and Q3, yeah, it's the same. So which means this force and this force equal, but the opposite direction. So which means F net is 0, and the situation change if QR is negative. as in the bottom figure. In this case, the two forces are equal in magnitude, but in the same direction. Yeah, you can see in the same direction, which means F net equal to F1 on 3. The magnitude of the force is given by Coulomb's law. Yeah, so like we just use this equation to calculate the force 1 on 3, like Q1, Q3, this is R. And just put the K here, Q1 here, Q3 here, and R here. And this is net force. This is an equal force due to Q2. So the net force on 1 NC. Sorry, I think there are something wrong here. It should, one is 10, the other is 1, so it should be 1. So I think you need to calculate it again. But like the net on the should be like twice F1 on 3. Yeah, you can calculate again. Yeah, to see if the result if it is right or not. Yeah, okay. Let's access this problem. Like this example illustrates the important idea that electric forces are vectors. An important part of assessing our answer is to see if it is reasonable. In the second case, the net force on the charge is approximately 1 m. Generally, charges of few NC separated by a few centimeter experience force in the range of a fraction of a million Newton to several million Newton. With this guideline, the answer appears to be reasonable. Yeah, you can after you recalculate, you can also use these assess steps to see if the answer is reasonable or not. Okay. Let's talk about the other example problem. Yeah, point charge A has a charge negative this one, and point charge B has a charge this one. They are separated by 1 centimeter. What are the magnitude and the direction of the electric force on charge A and B? Yeah, you can. Yeah, I think the answer will be easy. You can use this equation. And here Q1 is equal to this one, Q2 is equal to this one, R equal to this one. Like the force on each charge then is this one. This is the magnitude. Yeah, the force is attractive, so the force on each charge is directed toward the other charge. Yeah, this is what this question should be. Yeah, you can calculate this by yourself. Okay, let's check this question. Which is the direction of the net force on the charge at the lower, left? You can see here in this one, and from here to here they have this direction, and from here they have this direction. These two will have this direction, but here they have a bigger one, so which means it should have this directions like a net force. That makes sense to you. So the answer should be oh, sorry, yeah. Let me repeat this question. Yeah, because I just yeah, because this is the same same this is positive, this is positive, so it is a repulsive force. So this is this to this, and this is this to this, and yeah, so these two will have this force. Also, this is this to this will have the repulsive force because it's the same thing. So yeah, the direction for the net force should be B. Yeah, sorry about just now. Yeah, okay, let's talk about this one, which is the direction of the net force on the charge at the top. Yeah, here. Yeah, this one, you can see this one to this one, it will have this direction. And this one, because they are like opposite, so they will have the attractive force. So it should be this one. And then the net force should in this direction. So the answer should be D. Yeah, that makes sense to you? Okay. Let's talk about the other example, like comparing electric and gravitational forces. Yeah, a small plastic sphere is charged to negative 10, and say it is held 1 centimeter above a small glass bead at rest on a table. Here in the like the bead has a mass of 50 mg and a charge of positive 10 NC, will the glass bead lead up to the plastic sphere. And we will model the bead and the sphere as point charges and measure distance from their centers. There is an attractive electric force from the bead that will tend to pull the sphere upward. If this force is greater than the downward weight force, then the bead will leap up. Yeah, this makes sense. Okay, and we will start with a visual overview of the situation. The figure establishes a y. Here is a y axis, and identify the plastic sphere Q1 and the glass bead as Q2, and shows a free body diagram. The glass bead will rise if F1 on 2, because this is like opposite, so there will be attractive force. This force will be in this direction. If 1 on 2, if it is greater than W, and then it will rise. If this one is smaller than W, it will the beam will remain at the rest on the table. Yeah, because there is a table which tend exerts no more force on the bead. Okay, let's continue. Yeah, let's using the Coulomb's law to resolve the net force using the non-net force, the electric force. Yeah, here we know Q1 is 10, also 10, Q1 is also 10, and the key, yeah, none, and this is 1 centimeter. So this is the electric force, and this is the gravity force. Yeah, which means F 1 on 2 greater than gravity force. Yeah, extends the bead's weight by a factor of 16. So the glass bead will leap up. Yeah, the glass bead will leap upward. Yeah. Okay, the values used in these examples are realistic for spheres about 2 millimeter in diameter. These are small spheres that have been charged purposefully, giving charges in the NC range. In such cases, for small separations, the electric force is considerable, much larger than the weight force. Yeah, which means our result is quite reasonable. Yeah, like there are two there is another one example problem. 2.1 G honey beans each acquire a charge of this one as they fly back to their hive. As they approach the hive entrance, they are 1 centimeter apart. What is the magnitude of repulsive force between the two beans? How does this force compare with their weights? Yeah, the width of each beam is this one. Yeah, because this one, and the weight multiple the accelerate, and this is the weight. Yeah, this is the gravity force, and the pulsive force equal this one. Here Q1, Q2 equal this one, K equal this one, and the magnitude force on each beam is this one. So it is more than 10,000 times weaker than gravity. Yeah, so yeah, which means it will now affect the gravity situation. Yeah, so this is what we talk about in this class, and we will continue to talk about yeah, electrical fields in next class. Okay, thank you. Hope you have a good performance on example 2, exam 2. Yeah, okay. Bye. See you.